Okay, Assalamualaikum warahmatullahi wabarakatuh. Today our group will be presenting COximeter, early detection and alert. Moving on to the first part, which is problem identification. As we all know, carbon monoxide is an invisible, odorless, and also a dangerous gas when it's enter our body. So globally, there are about 1 million cases of carbon monoxide poisoning each year. So from this case, there are about 30 to 50% of misdiagnosed in early stage of carbon monoxide poisoning. So this will lead to more critical condition to the patient. So currently we have an arterial blood gas machine which can detect carbon monoxide in blood, but it takes really much time and also really expensive. Each of arterial blood gas machine will cost about 1 million ringgit. Let's move to our target user. Yeah? Group number 3. For the target users, we primarily target the paramedics, first responder and medical staff, especially in rural clinics, because they are the ones who are struggling with this problem. So the user need here, we got reliable detection of CO, portable, user-friendly, no blood sample need, and also low cost accessibility. So this is our benchmark, where we choose ABG machine as our benchmark. ABG machine can detect the carbon monoxide, but it's not portable, it needs blood sample to run, and also it's really high cost. Compared to our COximeter, we also can detect carbon monoxide, we are portable, we don't need any blood sample, and also we are low cost. Next, we are moving to the system architecture. So here is a 3D visual of our COximeter. The first one is what we call this is OLED screen that will display the measuring of carbon monoxide in body, and then we got the testing, we got microcontroller and also LED lights. These are one of main component in our COximeter, and then photodiode, also the battery. So for the stage, we got 3 stages, which is first one is input stage, where our multi-wavelength is emitted from the LED and going to penetrate our skin. So after it penetrates, the measurement will be taken by the photodiode and calculated by Arduino, also displayed in the display. So design specification, first of all, our user need. So we don't need any blood sample. In other words, it's non-invasive component. So how do we achieve non-invasive? We need to use multi-wavelength, which require a skin contact area. So our engineering target for this one is, the first one is 100% non-invasive. Second one is the fingertip contact needs to be below 12 centimeter square, and also we need to read the CO below 20 seconds. Next one, this is low cost. We are targeting to commercial it below 1,000 ringgit. And how is the design? We use the 3D pin casing, battery, Arduino, and minimal wiring components. And our engineering target for this, the battery to last about 23 hours usage continuously. Next, it's portable, which engineering target must be below 150 grams, and also climbing force is 0.3 meter. The last one is early warning alert, where the COximeter will give the warning when COHP is 50 seconds. Next. So this is design analysis, how we actually get the CO reading. The first one, finger will be placed in COximeter, and then light from the green and red LED will be emitted, and this light will travel through our blood and received by photodiode. So from this receipt, we can get the percentage of carbon monoxide. Yeah, this is some of the calculation. After the lights travel through our skin, photodiode will receive the average green reading and average red reading. From that, we can get ratio of carbon monoxide, and we do some calibration to get the percentage of it. So moving on to the design analysis, which is mechanical. Here, international medical, I think international medical standard require a 0.3 Newton. Okay, require 0.3 Newton force for the clamping. So we start with 0.3 force and we end up getting our spring need to be about 0.5 millimeter in its diameter for the clamping. Next one is for the housing, which we target the contact surface below 12 centimeters square, and yeah, we achieve that. The last one is electrical analysis. So before this, our engineering target is 23 hours of continuous use. So our usage is 55 milliampere. So we do some calculation here, we do ideal capacity and the over requirement, and we get the capacity that we need is 2000 mAh. Okay, we move into the task card. So the first task card is non-invasive safety. Non-invasive safety, where we use what we call it. It's 100% non-invasive and also require contact area below 12 centimeters square. So we achieve that one. The next one is diagnosis response time. So we already tried this COximeter to few of our yesterday, and alhamdulillah we also get the diagnosis time below 20 seconds. Okay, for the part is the we use 2000 mAh and the alarm trigger. So this is one of the students who got carbon monoxide reading 15%, which is critical reading in our carbon monoxide, and the alarm trigger here. And the last one is like we designed the total mass of our COximeter. The validation process and prototype will be after we finish this presentation. So for the social environment and economic impact, so we go to the public and safety. We convinced that this COximeter will reduce the mortality rate of CO poisoning by providing an early warning, and also we will bridge the gap for rural clinics who are unable to buy a BG machine. So ensuring all patients get equal access to diagnosis. Next, for the environmental responsibility, we align with SDG 7 and 12, which we also use rechargeable battery. And the last one, the material we use for the casing is PETG, which is eco-friendly material. Okay, next, economic impact and market fee. Our COximeter doesn't need any operation person, so we will save in operation. Also, manufacturing cost is efficiency and economic scalability for the medical is really wide. The last one is regulatory compliance. As I said just now, we follow ISO in 24, and the next one is medical standard. We ensuring the contact area is below 12 centimeters square. So for the complexity of the, we balance the paramedic need for speed result, which is below 20 seconds, and doctor needs for accuracy below 5% error. So let's move to the prototype video.
Assalamualaikum and what's up guys? So today we are going to describe our prototype. So let me give you a close look. So guys, we already put up our prototype. So we're gonna use my hand as the example. So we're gonna take like 10 seconds for the value to appear. So it happens to appear as much faster as I expected. So we're gonna still have to wait for the validation. So here we got myself 0% CO reading.
So Cairo got 0% CO reading. This one. The next one is we test our prototype on one of our yesterday. So today we are trying to do the prototype of our COximeter. a smoke grading. And this one is one of the finish up.
Remember.
Yeah, so that's
I think that's it. Thank you
Thank
guys.
you.
Any questions?
Anyone want to try first?
Yeah.
Okay. Can I get you design there? Okay. So the first user need no blood sample before the user need. Yes, because before this, the ABG machine will take a lot of time because they need to inject, they need to take blood sample from the patient.
Okay, so you want that one to be user need, right?
Yeah.
Okay, so give me an engineering target to say no blood sample. I'm gonna achieve that from my engineering target, and to do calculation or whatever that at the end I will come up with no blood sample.
Oh,
That's a feature fine, but I don't think that's related to your target that you're trying. I mean, this is yes or no. You want to do blood test or you don't do blood test? So I don't think there's an engineering target for that. Because given what you put there in the engineering target, you put finger clip contact 12 centimeters square. How is that blood or not blood or whatever? You know? That's actually should be something else. That's what the clip here for safety, like you put it in ISO, that's what needs to be for safe clamping, blah blah blah, or clipping or something. So it should be something else in the user needs instead of blood sample need. Okay? Then you have time to get CO below 20 seconds. That again from where? 20 seconds?
from
Why 20 seconds? Why not 10, 20, 50? It came from where that 20 seconds? Well, I can see it was from the ISO, right? Standard?
no, usually before this, the time to get CO reading is about, from the ABG machine, is take about 20 to 30 minutes. So we put target ourselves, we want to do it under 20 seconds. Yeah. Yes.
The other one, 50, 60 minutes. That's because they do blood tests and stuff like that.
Yeah.
So you were 20 seconds, just like that.
Yeah.
I don't know why, but anyway, fine. Big difference. And then the other one, the 12 is from ISO, the 12 centimeters square.
This one is from ISO.
That needs to be there for what I say.
Yeah.
This one low cost accessible, I don't know why that's 23 hours usage, less than 23 hours.
Oh, so
Yeah, but why 23 hours? I mean, people at least they go 24, you know, to say the full day. But 23, I don't know what's the number, 23 magic, that's my point.
Because like the patient with the critical CO readings need to be checked within like 24/7. So we can do like less than 23 hours because like we need 1 hour for it to charge because I usually use material. So you get my point, right? So the maximum capacity we can goes up to almost like 24/7, but we try to make it like logic.
No,
We get the one
it
hour.
should be 24/7. If it is 24/7, you just replace the battery. Or I don't know, or you do.
Yeah, we can charge it while it's
So that means that 1 hour, if I have some people, wait, I keep the CO until my battery charge. Anyway.
I get your point.
This one, the total mass, 150 gram. Why?
We like for this prototype to be like
Yeah,
compact.
but light. 100 gram is light, 100 is light also. Why 150? That's why I think this one mentioned many times before, still the same. So that 12 I can get, it's from from the standard. 22nd, okay, you are very ambitious, but it's okay. But it's less than the 30 minutes, so you're achieving a good target there. Right? This 0.3 Newton, I think also is from the standard. So that's what it needs to be, so not to harm blah blah blah. Okay? Notify when exceeds 15%. Again, what is that one? Why 15%? So if it is above, then it's okay. So that's okay, that also, alright? So you have to change. Another big thing here, I don't think you understood what I explained. Design characteristic is not the component, plastic printed case and battery, whatever. It should be the physical parameter that you're measuring. Alright, so for example, for finger clip, that should be the area, clipping area, or something like that, the characteristic. Right. For the other one, it should be the time, not required screen contact. That contact area, okay, that's okay. That goes up for the finger. But the time to get, that should be, the time to get should be your characteristic, not I don't know, wavelength or I don't know what are you doing there. Okay? Here you're talking about the mechanism. Here it should be like the force, the time, the power, the work, the rate.
Yeah.
Things that are measurable, and then you get the number here. Okay? Anyway, now can you show one design analysis? That's one component how you measure it. That's one. This one for the battery, right? So it started with 23 hours.
Yeah, we start here with 23
That's
hours.
your engineering target.
Our engineering target is 23 hours of continuous usage.
Uh-huh.
So we put 23 hours and also 55.
How you get that total system current is 55
We do the calculation back here.
No, but the calculation based on you chose already what is Arduino, what type of this. But then you have to first select them based on your calculation before you decide. Because here you decide, I'm taking ESP32. Why ESP32? Why that OM sensor, that specific one? You know, that's what we get. Any component you have to justify getting it from the engineering target. Because now you choose the component and then, okay, let me try now, it works or not. Let's do the calculation, yeah, it meets the okay. You know, that's not the design that I told you, similar to the previous grade. So you should start from some engineering target. For example, I don't know, the 12. Can you get me like the 12 centimeter square? Where did you use it in your calculation? Here, right? So you said my target is 12. Okay, let me pick this, and calculate. It's 3 centimeters, so it's less than 12. That's not the way. You should start from 12 and then find. So what are you finding here? L and W. What are the LW? The contact. Yeah, so that area should be 12 for me. You should start from the area is 12. Now find the LW. Because that's the LW, that's what for your casing or whatever, the module, the equipment, etc. Understand? So the analysis should be from the engineering target, link it to some of your parameters related to your components, and then deduce some of them. Assume maybe one, get the other one, etc. Then it will be designed based on your engineering target, not that. Okay? Alright, one last thing. So it's nice, I can put there it tells me 15. How do I know it's 15? I'm going to put my finger.
Okay.
It's finger, right?
Okay.
Right? Okay? What is it? I want to try actually. Maybe I have a lot of CO, I'm not aware of it. I'm not smoker, I'm not using it. I'll see you if I something that to me. Yeah, I put there.
Yeah, you put it on the sensor.
Green light.
Wait, you still need to wait for 10 seconds for it to, you know.
Okay,
You put your finger on the sensor. What is the shut down?
It can be any finger? Any finger, right? Not it has to be the thumb or anything, right?
Okay.
I
think yeah, because this cables and this prototype is not compatible. Like this is used like 3.7 volts, but this one use 5 volts the minimum.
Okay.
So it's overload. So the thing is
So
shutting down.
when did you try it? How did you try it?
We direct it with the power source.
Okay.
You use charger.
All right. Anyway, so it works or does it work now? Should I try or not?
Yeah,
try?
you should try with it. Okay.
Where?
Place
Here,
your
the
fingers
sensor?
and then the little camera.
On the sensor.
Okay.
Bismillahirrahmanirrahim.
Depan.
Wait.
Oh yeah.
We'll just a bit.
How many seconds already?
I don't know. My hand they get tired already. I'm very tired.
I think
now.
you need to.
Oh, still.
The calibration I think is off. I think you need to.
It's okay.
check
It's okay.
the-
Anyway, but then it will work, right?
Yeah, it will work.
You can give me a number. Let's say it gave me 20 now. No, 20 is too much. Let's say it gave me whatever, 5, 10, is too much. It is 20, for example. How do I know it is correct? Do you remember?
Maybe if someone will get CO above 20%,
No. You need to do some validation beside the validation because you evaluate new product. Right? I don't know whatever you use, the sensor or whatever to measure the CO or whatever it is.
We get the article, the medical article, take like absorption value for different ppm that every level of carbon monoxide potential. So and we get and then we use the grid envelope to calculate and then get the percentage.
Okay, fine. All that I have no issue. I see it is working, it gives some number. Like I do simulation, I put number, I will get something also. How do I know that it's correct? Because you might did some mistake in your programming, maybe in your conversion, maybe the sensor it has to a certain level. My point is, when you divide new things here, you have to compare it to something reliable. What is reliable? So ideally, actually, if I go for you, I will go for one case that they do that machine in the hospital, and that which is calibrated and we know. And the same guy without blood, I can do here, and then I see if you get, let's say 15, I get 14. It's okay, mine is actually accurate by 10%, 1%, something like that. I get 15, oh, 100% accurate. Right? He gets 15, I get 0, then your thinking is completely off. You understand? Because here I can make whatever circuit and stuff and they get numbers. It's the same the other guy when they did the app. So if you have to have it really genuine, I mean, this is really not now. Now, you say it is working. I want to ask, but if this will work for the max, you have to prove that it is accurate. Or it has some accuracy, 5%, 10%, whatever.
yes, because we have done this test, and also there are articles that show that if a normal person, they will have CO reading below 6%, and for the smoker, they will get 6 and above until
No, but
50.
if not a smoker, let's say, I went for jogging this morning, and the guys they were burning a lot of things around the house.
Yeah.
I smoke without smoking,
Yes.
So I think, I'm healthy, and then you might have had some CO. That's okay. It will give you maybe roughly that it is water or not. But still it's not that. So if you want an accurate one, you do this one. Something that I know the accuracy, almost like what the standard uses, mine I compare it to them. And then I know how it is. Then if you get very close to that measurement, then it's very good. So I can invest in this one and we can start our company. Okay? All right. Thank you.
But if you really want to try, you can put the charging port and then you can put it
Yeah,
in.
it's okay, but if you stay here after, otherwise you're going to miss out now. 6 o'clock.
Oh, we have another question.
That's it. This is group 3, right?
No more question? Supervisors? Okay, thank you.